So in this chapter, we'll talk about the diffraction phenomenon. So diffraction is basically is a kind of wave phenomenon. Okay, it's a wave phenomenon, we can say, and okay, a wave phenomenon. And these wave phenomenon, we say these are for say for example, this could be true for any kind of electromagnetic wave. Okay, it could be the sound wave, or it could be the wave in, or it could be the, say we can say it could be the wave in water. Okay, wave in water. So these are the phenomenon. Okay, so the picture you see here, this like this beautiful picture you see here, this one and this one, this picture is the because of the uh, because of because of uh, diffraction. Okay, diffraction of wave, diffraction of waves. So let's go further and we talk about what is diffraction. Diffraction is basically the bending of wave around the edge of opening or the obstacle. Okay, so just take one example over here. Say we have, say I have this source of, I'm taking, this is the source of this light. We can take any light, maybe yellow, green, blue. Okay, and I drew a line like this. Okay, and this is a screen over here. Okay, this is a screen. Say I put at that point, say this is the obstacle. Okay, this is a obstacle. We can say this is an opaque object. Okay, opaque object. Okay, so if we consider the light travels in a straight line, then in that scenario the region below down is called the geometrical optics. Sorry, geometric shadow. Okay, geometrical shadow. So means basically we'll say this region will be dark. So based on this region will be completely dark, and we're considering because of the optics, we're considering up to this point, we call it geometric optics. Based on that, because light travels in a straight line. Okay, so this means in that part we are considering that light travels in a straight line. Okay, a straight line. But in actual case, the small region here at that point, small region, we can consider this small region over here. This small region is not completely going to be dark. This region we see is not completely dark, and it is a image. This size, this region looks like it like a blurred, okay, blurred edge. So this is because of the because of the diffraction of light, of electromagnetic wave. Okay, so bending of light when there is a small opening or there is an edge, this kind of phenomenon is called the diffraction of light. Okay, let's see one simulation we have. Okay, so we'll see that simulation now, and we'll see that. Okay, here you see there is a small opening over here. let's start the simulation. Light or the wave is bending in that region. If you see here, you can clearly see that. You can clearly see in this region. In this region, the wave is bending. You can see. Say I'm changing this color. Say for example, blue and green. You see one could be trough, other could be crest. We can change the slit width, the opening hole, right? If you change the opening hole, the pattern also changes. So so in all case, whether slit width means this a small opening will be bigger or smaller. In that scenario, it could be bigger or it could be smaller, but you see light is bending. Okay, we can say, we can use the color, we can pause it. Okay, so you can play with the simulation. So telling that it is a way we're going to bend in the corner. And this bending of light can be explained on the basis of the Huygens principle. Okay, so what it says, so we can again draw the same picture that I drew before. This is the obstacle. Okay, so if we suppose the wavefront coming at that point, okay, so this is the wavefront. So according to this principle, according to this principle, every point on the wavefront behaves as a source, right? So this every point. So this is also a source. This is all 2 is also a source, 3 is also a source. So every point, okay, this point behaves as a sources. If this is the sources, what will happen? It again emits the light. Okay, this again emitting the light. Say for example, this dot behaves as a source, it emits a light. This dot behaves as a source, it emits a light. This other source behaves as a source, they emit a light. So in that way, when it comes to a screen, then it comes to a screen at that point, then because of the interference between wavelets or secondary wavefront, or is also called secondary wavefront, they interfere. If they interfere, we know that this region where they interfere, this region, the intensity of light gets changed, or intensity of light gets modified. So what does it mean? As before, we can see a band of light. Say this region is bright, this region is dark, this region is bright, this region is dark, kind of thing. So this diffraction phenomenon is because of the interference between the wavelets from the single wavefront. Okay, so in actual sense, we can say that interference and diffraction go together. Interference and the diffraction go together. Okay, go together. And it can't be separable. So sometimes we can see interference pattern more enforced. Sometimes we see this phenomenon, diffraction phenomenon, is more enforced. Okay, but it happens all together at the same time. So in our everyday life, the diffraction of sound is easily observed, but the diffraction of light wave cannot be easily seen. For example, say we are in this room. Okay, this is our room. Okay, so say we have a door over here. This door is open. Okay, so we have door is open. Say we have two people sitting. One people is just near the door, in front of the door. Your friend, the other person is just here. So person A and person B. So if you look at that part, we can say that they can hear each other. They can hear each other, but can't see. Okay, so in this case, in this case, they can see, they can hear each other because of the diffraction of sound wave. Okay, and they cannot see because very difficult to see the diffraction of light. So there is a rule kind of thing is if the wavelength we generally represent by symbol lambda, okay, is nearly equal to the size of the obstacle, or we can say it is slit. If this is the condition, then diffraction could be observable. Okay, diffraction could be observable. If not, then there is a diffraction, but we cannot see it. Okay. Let's talk about the single slit diffraction kind of thing. Okay, single slit. So you see that if there is a single slit, this is a single slit, and its width is A. Width of the slit is A. And if light passes through this, so this means a light electromagnetic wave can pass through this hole or a small opening. Okay, then what will happen at the center? We'll see bright. This is the central bright. Okay, then we see first dark in the both side. First dark. Then again we'll see the bright. We call it first bright. Okay, and this one is also first bright. And this kind of alternate band keep going, okay, to the both side of the center bright. But you have observed here that the width of each bright spot, you see here, is not same. Okay, you see here center bright is more intensity is very high. Okay, then if you go to the first position of bright, intensity is going down. So you see intensity of first of this center bright is very high. The intensity of first bright is going down. Okay, so in the case of this case diffraction, the intensity of each bright is not same. Okay, so we can see the simulation we have seen before. Let's see again. So if we have the single slit, we can change the distance between the slits. And okay, so I'm going to change the slit width. You can see here, if I change the slit width, the intensity and width of the brightness also changes. If I change the distance between screen and the source, it also changes. Okay, so this means you see from this point that this this width of the center bright, first bright, also depends on this the distance between distance between source and screen. This is the source. Okay, so this light is coming through this point. So this is the region of source. Okay, the distance between source and the screen. So we are observing this pattern over here. So this is the screen case. This is the screen. Okay, it also depends on this distance. It also depends on the width of this screen. Okay, let's check when we did similar thing in the experiment. If you remember the Young's double slit experiment, Young's double slit experiment. Okay, if you remember, intensity of each brightness will be same, just like that. Okay, so say for example, this one is the central bright. This intensity and intensity of first bright. Okay, intensity of first bright, intensity of, say, this is also first bright to the both side of the central bright is same. But in the case of single slit diffraction, we see that intensity is not same. This is the central one, intensity is very high. If you consider the first one, intensity goes down, just like this. Okay, so this you can also observe in this kind of simulation. Okay, in the case of interference, you see that the intensity of each band is same. Okay, but if we consider just for the single slit, the intensity level will not be same for each position of brightness. Okay, this is the key concept over here in the case of the diffraction case. Okay. Okay, so let's move further and see. We are talking about Fresnel diffraction and the Fraunhofer diffraction. Okay, so in Fresnel diffraction, the source and screen at finite distances from say slit, or we can say it is a obstacle. Okay, obstacle. So for example, say I have this small slit, okay, and I have a source. So I'm putting over here. This is source. Say for example, this is a yellow color coming from this light. It's called laser, yellow laser, just giving the yellow color. And this behaves as a source. And to find the pattern of the diffraction, we put the screen over here. So this means in this case, the source and the obstacle are at finite distance from the slit. Okay. So this is the position of slit. But in the case of Fraunhofer diffraction, only difference is that we have the slit over here. Okay, slit over here. So again, we have the source. So this is the source of light. Okay, and again we have the screen. We are assuming that this distance, this distance between source and the slit is actually very far away, very far, and we can assume as is as infinite. Similarly, the distance between slit and the screen is also very far away, we can consider as infinite. So in the case of Fraunhofer diffraction, source and screen are at infinite distances from slit. Okay, so this means to focus the light on the source, to focus the light, we have to use the lenses. Okay, we can do that. So we further talk about this Fraunhofer diffraction. Okay, so let's see. And in the case of Fraunhofer diffraction, okay, just wait a minute. Okay, so in the case of, say, let's talk about again Fraunhofer diffraction. In this case, we know that, say, this is a single slit. Okay, just one hole, one opening. Be careful that this hole looks very bigger, but in actual practice, this opening is very small. Okay, so we should be careful about the opening. Very small, very small. Okay, means this opening. Say, you know that if the source of light is very far away from us, then plane wave front will come in. So these are the plane wave front. Okay, because in our case, source is at infinity. So, you know, we defined as before that a perpendicular line to the wave front represents the rays. So these are the incident rays. Okay, so you know that each point of the wave front behaves as a source. So these are the sources. So we know that this is the screen. This is the screen. Okay, so we generally put say lens. Say we put a lens, for example, we put a convex lens. So this light, when you know that each point of this slit behaves as a source. So from this source, you can get a ray just like that. Okay, and after refraction through the lens, maybe they all meet at some point. Okay, just like that or somewhere. So this means in this case, this is the focal length. This will be the focal length for the lens. Okay, so we'll use this concept to explain the spectra, to explain the spectra we get in the Fraunhofer diffraction. Okay, so let's move further and explain this thing in more detail. Okay, so we are focusing on this part. Okay, so let's see here that you know that each point of the wave front behaves as a source. So that's the reason I just put 4 dots. So each dot behaves as a source. If this is a source, then what will happen from one, if this all one is also a source, it will emit light everywhere. Okay, so this is the wavefront like this. Okay, if I consider the point 2 as a source, it also emits light everywhere. Okay, these are the rays, and this is the, you can say this as a wavelets. Same case is true for that. Same thing, if we consider the point 3, it also emits lights everywhere. Okay, this is the wavelets, just like that. So each point of the wavefront we have as a source. So at first we will consider, say, if we have point source 1, point source 2, point source 3, and point source 4, and so on, we know that it emits light everywhere. So at first, we'll consider the case when theta is equal to 0. What does it mean? The light emitting from every point is parallel. We are just considering this part, this kind of light. Just be careful that it will emit light everywhere. We are just now considering this kind of ray, which are all parallel to each other. Okay, this means it's parallel to the say, for example, we are considering the light which are parallel to the axis. So what I mean by axis is like this. It is the source and this is the screen. Okay, this is the source. Then if this is the, we are considering the rays parallel to this line, means we join the center of the source and where we get the central bright. Okay, if we are considering this case, this means in this scenario, because of the lens, it will take same time to reach on the screen. So if this is the case, what will happen? What will happen is that in this case, the rays heading towards a common destinations are all parallel. When they travel straight ahead, as shown in picture, they remain in phase and we observe a central bright. So what does it mean by central bright? Let's see again the picture we have seen before. Okay, so in this case, say for example, if this is the point, each point we consider here. So this means if this is the screen, this light also takes same time to reach here. This also light takes the same point reach here. So they're all in phase. So light coming, reaching to the screen are all in phase. That's the reason we get the central bright. Central bright. Okay. This is the first scenario. Let's consider, we are considering the different situations. Say, in this case, say the rays from the bottom travels a distance of one wavelength further than the rays from the top. What does it mean? Light emitting from the top and light emitting from the bottom has a phase difference. We can say in terms of path difference of this much, lambda. Okay, lambda. This means what? In this case, say in this scenario, we are considering the rays. Say for example, this is the point first, this is the point second, this is the point third, and see, in this case we have to consider the rays just like that, not parallel to the axis as before. Okay, so now it is making an angle theta with the parallel line. Okay, so this means a ray from the center travels a distance, in this case a ray from the center travels a distance lambda over 2 less than the 1 point at the bottom of the edge. So what does it mean here is this? Okay, this means we have this slit. Okay, so we know, say, 1 point is here, 1 point is here. So in this case, because of these two extreme points, if we consider 1 point here, 1 point here, then if we consider these 2 points, one at the top, one at the just below this point, then in this case, path difference will be lambda over 2. For this part, I'm talking about this point and this point. Okay, say for example, this is point 1, this is point A, this is point B. So say, but be careful that path difference for waves traveling from A and C is lambda, A and C. So this means we are considering this kind of range. Okay, so this means if they interfere, these will produce a destructive interference. Okay, then where this interfere, this point will be going to be not it is the destructive, so it will be dark. Similarly, if we consider the other point, so I'm considering the other point here, say I'm considering 1 point just down the A, other point with down D. So again, they say I will call point A prime and we call it this B prime. So again, they will interfere destructively, and here they meet and they produce as the spot is this spot will be the dark. So what I'm saying here at the end, the effect of the upper half and effect of the lower half will going to cancel each other. So in short, we can say effect of upper half AB cancels effect of lower half BC. So because of that, the point in that situation, this point will be dark. So that's how we are explaining up to this point. Okay. So as before, we can find the path difference between these two will be A sine theta. Okay. So if this is A, if in this case, if A is the slit width, okay, then path difference between the wave emitting from this point and the wave emitting from that point will be A sine theta. Okay. If we do this point, up to this point, next consider the case. Next consider the case. I'm considering these 2 points. Now consider it could be anything. So consider path difference, in this case 3 lambda over 2. Be careful that in this case, path difference between the wave emitting from at this point and at the bottom point, in this case, path difference equal to this value lambda. Okay. So we are changing, we don't know. It could be anything, lambda, 2 lambda, 3 lambda. So we will consider all the options. So basically we are considering all options. So basically we are considering options like lambda. Maybe it could be like 1.5 lambda. It could be 2 lambda and so on like this. So now we are considering 1.5 lambda, which is basically 3 lambda over 2. If this is the case, what will happen? we can divide this slit into 3 parts. Okay, so this, if we divide equal into 3 parts, what will happen? The light emitting from this point and light emitting from the this point has path difference of this value lambda. Okay, be careful that the path difference from this point and this point is this path difference will be 3 lambda over 2. Okay, so in this case, the effect of those first 2 half, they cancel each other, and this the remaining part, third part, will produce the constructive interference. So this means in this case, the light traveling, we are considering maybe this angle may be different. Say we can say this angle is theta 2. Okay, so in this case, even though we say the symbol, we use the same symbol theta, in this case, say we have this angle theta is equal to theta 1. So in this case, the all light travelings with angle theta 2 will interfere in such a way that we get a bright interference, but we are not getting equally bright. The reason is that first 2 half, the effect of this half is balanced by the effect of this part. So only we have this 2 half cancel each other. We are only remaining with the 1/3. So this means, say, one ray travels a distance lambda different from the ray from the bottom and arrives in phase and interfere constructively. 2 rays, each from the slightly above these 2, also add constructively. So most rays from the slit have another ray to interfere with the constructively, and the maximum intensity occurs at this angle. So at this angle means the angle is different at this time. So however, all rays interfere constructively. For this situation, the maxima is not intense at the center. Okay, so the key point over is that if we divide the slit into 2 parts, the effect of this half, this part, is balanced by effect of this part. So they cancel because here the wave emitting has this point, the wave emitting from this point and wave emitting from this point has path difference, this value lambda. Okay, so this region basically produce a destructive interference, destructive interference happens. That's why they will not contribute for the bright one. So bright one is contribution from this part. So this part, this gives contribution for bright. But be careful that all part will not give the contribution for the bright. So intensity is not same as the bright at the central part. Okay, so this will give you the path difference. When path difference between at the top point and bottom point is 3 lambda over 2, then it will then in this case it will interfere constructively, so only for the part, and it will give the bright interference. Okay, similarly we can consider the other situation here. Say in this case, say path difference is 2 lambda. 2 lambda from light emitting from this point and light emitting from this point. Okay, so in this case, again as before, this will give the destructive interference. So this is the position for second dark spot or dark fringe. Okay, so if we keep doing just like that, what we observe that to obtain the destructive interference, we figure out always that d sine theta equals m lambda. So for example, if the path difference we see as before, let's see here. Here we just say the slit width, we can say this as a D or A, it doesn't matter any difference. Okay, so just write A. Okay, so if the path difference, we figure out that if path difference is A sine theta equals lambda, in the first case, we get first arc. Okay, when we have A sine theta equals to lambda, so this case, then we have second arc. Okay, similarly, so this means if we have if you keep going just like that, then if we have A sine theta equal to m lambda, then we get the destructive interference. Okay, so here A is the slit width and lambda is the light's wavelength and theta is the angle relative to the original direction of the light. So this angle, we can say theta 1, we can say this angle theta 2, they are all different. Okay, so this will explain all about this diffraction of light. If we are keep going like this, so if you so we see that this is the central bright, this is the central bright, this is the first bright. Okay, so this is the first dark, this is the second dark. Again, if you go to other side, this will be first dark. So, but the question is, we are plotting here intensity and sine theta. So, for example, A sine theta equals lambda for first dark. Okay, so this means sine theta equals lambda over A. So these are the basically the value of sine theta. So this is the value of sine theta. We can say this is the value of sine theta 1, and this is the value of sine theta 2. This is the value of, say, sine theta 3, just like that. Okay, this is the value of, to the other side, it will be the value of sine theta 1. So this gives this gives the pattern how intensity looks like in the single slit. Okay, if you understand up to this point, you can solve this problem based on, they give you the wavelength, they give you the angle, then we have to find the slit width, and we can find at what angle is the first minimum is going, we'll get that. Okay,